The drying rate develops a bit differently during the drying process depending on if the drying goods is hygroscopic or non-hygroscopic. If we start with the surface wet material, both kinds of material behave in the same way initially. The air we dry with is in essence only in contact with water. Since the surface of the water remains essentially constant, so does the drying rate. Thus, in a plot with the water content in the drying goods on the x-axis and the drying rate on the y-axis, the drying rate is simply a horizontal line, starting from the right and going to the left. We call this part of the drying process the constant rate period. As soon as we reach a point where some fraction of the surface is dry, however, the drying rate will decrease. We call the point in the drying process when the surface is no longer fully wetted the critical point. The period after the critical point, that is the period during which the drying rate decreases, we call the falling rate period. For a non-hygroscopic material, the drying rate decreases linearly during the falling rate period. The longer the drying continues, the less wetted surface remains, and after a while all water being removed needs to diffuse out from within the drying goods before it can be taken away by the air. There are no forces between the water molecules and the material to overcome to evaporate the water inside the drying goods, so the water molecules simply need to evaporate and then diffuse out. The lowest water content, possibly zero, that can be reached is the same regardless of the relative humidity of the air. For a hygroscopic material, there are forces between the water molecules and the material to overcome, and the lowest achievable water content will depend on the relative humidity of the air used. How fast the drying rate will decrease during the falling rate period will depend on the nature of the forces between the water and the material. And the shape of the curve might be piecewise linear, non-linear, or some combination thereof. But what we can say for certain is that it will not be a straight line all the way down to a drying rate of 0. So let us now test your understanding of drying. How do the conditions in the bulk air change along an adiabatic dryer? And how do the conditions of the air close to the surface of the drying goods change? In these diagrams for countercurrent and co-current dryers, draw the bulk air as thick lines and the air close to the surface as thin lines. Use TW to denote the wet temperature of the incoming bulk air and XW to denote the water content of an air with that wet temperature and a relative humidity of 100%. I'm not surprised if you find this difficult, but please pause here and see what you can figure out yourself. Okay, let us begin with drawing the thick lines for the temperature of the bulk air. It is difficult to say exactly how the conditions will change along the dryer, but we know that the temperature will decrease, since the state of the air follows the adiabatic cooling line in the Maillard diagram. So we just draw a line like that. As for the water content of the air, we know that it will increase. Okay. The temperature of the drying goods may start at a temperature lower than the wet temperature of the bulk air. That is, if the drying goods haven't been preheated enough. When the temperature of the drying goods reaches the wet temperature, or to be more precise, the adiabatic temperature, we are now in the constant rate period, and the temperature will remain constant until the critical point when the surface becomes partially dry. In the falling rate period, evaporation will be slower, and thus the drying rate will be slower, and the drying goods will begin to heat up above the wet temperature. How much and how rapid will depend on the remaining moisture and the temperature and moisture of the air. Regarding the water content of the air, close to the surface of the material, if the drying goods have not been preheated to the wet temperature, the air close to the surface will initially have a lower water content than XW. Once the temperature of the surface wet material has reached T-wet, we are in the constant rate period, and the water content in the air close to the surface remains constant at XW. After we have reached the critical point, where the surface becomes partially dry, the evaporation rate decreases and the water content in the air close to the surface starts to decrease. The driving force for mass transfer is dependent on the difference between the water content in the bulk air and the water content in the air close to the surface. The driving force for the heat transfer is dependent on the difference between the temperature of the bulk air and the temperature close to the surface. The drying rate is in turn determined by the simultaneous mass and heat transfer. Now I recommend you to try to let this sink in a bit. Can you see the connection between the drying rate graphs and these graphs over driving forces for mass and heat transfer? Finally, to test your understanding, pause the video here and try to figure out whether co-current or counter-current dryers are best for A. Heat-sensitive materials, B. Hygroscopic materials, and C. Heat-sensitive hygroscopic materials. In a counter-current dryer, the temperature of the material can reach higher temperatures than in a co-current dryer. A co-current dryer is therefore better for heat-sensitive materials. Note, however, that in a co-current dryer, the almost dry material is in contact with an air with high relative humidity. So if you have a hygroscopic material that you want to dry to low water contents, a counter-current dryer is thus better than a co-current dryer. If you have a heat-sensitive hygroscopic material, like for example milk powder, there are pros and cons with both dryer designs, and there is no simple answer on what is best. Thus, for heat-sensitive hygroscopic materials, you typically want to design the dryer really carefully so you get a suitably dry product of good quality.